I refer to these as roadmaps, although you guys might not see why it looks like a roadmap. This is a very condensed roadmap, like one starting material and a bunch of different directions you can go. If you look at your practice finals, the past finals that I've given, those roadmaps often have connections of reactions that just keep going. We're in a limited spot right now because we're only looking at alkene addition reactions right now. But starting next week, we're going to look at alkyne reactions, substitution reactions, elimination reactions. So this stuff then starts to be able to become a series of steps that can just keep going. Remember I showed you guys some examples of total synthesis, like taking a 6-membered ring and making cholesterol, which has 6 rings in it. No, 4 rings in it. So these roadmaps are something I want you to be familiar with. Taking our alkene and going to the top, what Chloe recognized was an epoxide forms. That's important. If you don't recognize it as an epoxide, you're not going to be able to recognize what change is happening and what reagent is necessary. So an epoxide forms, and she knows that to take an alkene and make an epoxide, we need MCPBA. And the question was, do I have to put MCPBA and RCO3 in parentheses? No. You could either put MCPBA, which is a type of peroxy acid, or you could put RCO3H, which is generic for peroxy acid. It doesn't matter if you actually have a real peroxy acid or just this generic version. But earlier, Andrew had put X2 as the reagent for this reaction, recognizing that there's a dihalide, vicinal dihalide that's formed. He put X2 because that's what's on the reaction chart that I gave you. But X2 doesn't tell me which halogen. It doesn't matter which peroxy acid is being used. MCPBA is just the most common one. But it does matter which halogen is being used because I'm specifically getting a dibromide, a dibromo compound. So X2, not the best answer here because I can be more specific about what type of X2. This is actually one of the challenges that I run into in giving those reagent sheets out. Should I put X2 and show you what it looks like generically, or should I put Cl2, Br2, I2 and show you what each of them looked like? I would say I want to give you the generic form, but I want you to be able to apply it with a specific form. Does that feel like an okay compromise? I give it to you as a generic form, you apply it in a specific way. Okay. Br2 is an anti-addition reaction. So if this stereoisomer forms, where the bromines are anti to each other, I should also be able to get the other stereoisomer, where instead of the bromine on the left being dashed, the bromine on the left is wedged. The reaction to the left is ozonolysis. What type of ozonolysis? We have 2 types, reductive and we have oxidative. This is reductive, meaning if there are vinylic hydrogens, if there is a hydrogen bonded directly to the alkene, that hydrogen will not be oxidized. That hydrogen will stay on the carbon as a more reduced product. But if this carbon is treated through oxidative ozonolysis, H2O2, then this gets oxidized into OH. So we get cleavage and 2 carbonyls. On the left, I create a ketone because that carbon of the alkene is already bonded to 2 other carbons. So my alkene gets cleaved, I get a ketone. On the right, I get an aldehyde because that carbon is bonded once to a carbon and once to a hydrogen. So that carbonyl version becomes an aldehyde. All right, so solving the other things that are remaining. On the top, My epoxidation is syn addition, and because I've created two stereo centers, there are two versions of this product that might form. The epoxide might form on the top face. The epoxide might form on the bottom face. Sometimes we don't show stereochemistry. For instance, on the roadmaps that I give on exams, I usually say you may ignore stereochemistry. You're looking at just the product that forms and not the stereoisomers of it that form. If we wanted to draw this product but ignore the stereochemistry, it becomes a lot easier because you don't have to think about all your wedges and all your dashes. You just draw the functional groups where they are. All right, the one on the right, what type of reaction has occurred? Can you tell me? One more time. It is not hydrohalogenation because, there you go, there's no halogen in the product, right?
That's what was in my head.
Hydrogenation or hydrogenation. We're doing hydrogenation and the reagents necessary, H2 with a palladium carbon catalyst. We know that hydrogenation is syn addition, but this reaction only produces one stereocenter. In one place, the hydrogen is added and becomes a chiral carbon. In another place, a hydrogen is added and becomes a chiral carbon. So the missing product here, again, is just the missing enantiomer. Some of these reactions produced two stereocenters. Halogenation made two stereocenters. Epoxidation made two stereocenters. Some of these reactions made one. Hydrogenation made just one stereocenter. And one of these reactions made 0 stereocenters. And how many stereocenters were in the starting material? 0 chiral carbons, but that alkene is a stereocenter. The alkene is currently in a trans configuration, but if the methyl and hydrogen swapped, it'd be in a cis configuration. That's a stereocenter, but not a chiral center. All right, the roadmap on the right is a little bit more challenging. To solve this one, we actually have to take information we already have about the products and work them backwards to figure out what alkene must be missing. This product, the 2 carboxylic acids, you've only seen one way to make a carboxylic acid, and that's by oxidative cleavage. So there's good reason to suspect that this will form by oxidative cleavage. That is further confirmed by the fact that the same starting material can make just one long carbon chain. So my starting material must be one long carbon chain if this reaction just creates one long carbon chain. And that long carbon chain can be cleaved. What I'm going to do is map my carbons so that I can see exactly how those carbons from my starting material end up in both of my products. Or another way of saying this, I can confirm that this product has the same number of carbons as this product. All right, well, the reaction that produced this product up here, hydrogenation. It's the only thing that makes sense because hydrogenation is the only reaction that leaves us with just alkane functionality. Well, this hydrogenation didn't leave us with just alkane, but that's because this is not just an alkene. The carbonyl stuck around as well. So hydrogenation, it couldn't have been hydration. There's no alcohol. It couldn't have been diol addition. It couldn't have been halogenation. It couldn't have been haloether. It couldn't have been halohydrin. Could have only been hydrogenation. But where was the alkene? There's no way of knowing just from this one. The alkene could have been between 1 and 2, 2 and 3, 3 and 4, 4 and 5, 5 and 6. The alkene could have been in multiple places. In fact, this triene reacts with the same reagents to give the same product. So with just this information, I don't have enough. But Andrew?
Yeah, because that's where the alkene broke in half was between 3 and 4.
This product tells us information that this product couldn't have. 3 and 4 were the alkene carbons. How do we know that? Because anytime you cleave a carbon, anytime you cleave an alkene, it's the 2 carbons of the alkene that become carbonyl carbons. The alkene carbons become carbonyl carbons. The carbonyl carbons were alkene carbons. So I'm going to draw my long carbon chain again, and I'm going to draw an alkene between carbons 3 and 4. All right.
Why are there 7 carbons? I think you did an extra carbon. Or did we get 1?
Yeah, I sure did, right here. I think up there I added extra carbons too. Yeah, that was my first mistake, was having too many on that example. This was something I meant to say yesterday, and I didn't write it down on the board to get it into your notes. Hydrogenation does not use coefficients. We don't care that much about stoichiometry. Hydrogenation always assumes excess H2. Because we always assume it, we don't say it. I think you guys can see that taking a triene all the way down to alkane, that's not using 1 equivalence of H2. That's using 3 equivalences of H2, but you'll never see anyone report it that way.
Well, doesn't really matter. What is that? 2,5-methyl hex 1,3,5 triene.
2,5-dimethyl hexa 1,3,5-triene. Yep.
So hydrogenation is the only one that can form alkanes out of all of them?
Yeah. You saw how all the other functional groups, or all the other reactions, formed some other functional group. Formed some sort of halo group, formed some sort of alcohol, formed some sort of epoxide or carbonyl. Hydrogenation's the only one that took it down to an alkane. All right, so here's what I'm thinking, is that I've got an alkene between carbons 3 and 4. Is that the only alkene possible that can form between carbons 3 and 4? Remember the other day, I had on the worksheet this structure, and I asked you guys to predict what alkenes could be made from that alpha carbon with the bromine and the beta carbons on the other side. And it was obvious right away that you could form these 2 alkenes. That came up super fast. And then I pointed out there was a 3rd alkene you could make. Do you want to explain more then?
The terminal one off the top.
The terminal, I did make the terminal one here. That's not a carbon, so I can't make an alkene there. Actually, that's a pretty common mistake, is that people will accidentally erase something but leave the bond and create a new carbon, right? What was the missing alkene possible? The terminal on the right is too far away. It'll have to be a carbon bonded to this carbon. This carbon will be part of forming the alkene. So this one is too far away. Even if it did, That's just this structure, 1-butene. What was the missing one? You've got it in your sheet at least.
Actually, only wrote those two on the sheet.
Oh no. Good time to add it to the sheet. What's missing? The fact that this trans alkene could have just as easily been a cis alkene. That's what's missing. Is this the only alkene possible between 3 and 4? It could also be its cis alkene. This is a trans alkene. Its cis stereoisomer is also a possibility. And we do not have the information necessary yet because hydrogenation didn't create any chiral centers. And oxidative ozonolysis, sorry, I didn't add the reagents, O3, H2O2, or hot potassium permanganate. Neither of these reactions depend on the alkene being cis or trans. Both of these reactions work just as well whether the alkene is cis or trans. And whether the alkene is cis or trans doesn't impact the acid catalyzed hydration on the left. But when we go downward and we look at this syn-diol addition, I've given you this requirement. I'm looking for a meso product. And that may depend on the version of the alkene that we have. Gavin, you had a question?
Yeah, is that the E2-butene or the bromoethylene? On the top right, the orange. Where is that?
This is E2-butene, and this is Z2-butene. And bromoethylene was this compound. Okay, syn-diol addition, OSO4. We can start by just copying down the carbon chain because the carbon chain is not going to change in this reaction. We're not adding carbons, we're not losing carbons. At carbons 3 and 4, I'll get an alcohol, a vicinal diol. And whether I draw them wedged or dashed, they just need to be syn to each other. If my alkene is this trans alkene, this is what the syn-diol addition looks like. But if my alkene is the cis stereoisomer, okay, once again, I'm just going to copy down my carbon chain. I'm going to draw my carbon chain exactly how it looks. And I'm going to consume the pi bond. It's not trans. This is syn-diol addition. Right? So as long as the carbon chain looks exactly the same, no zigzag to zig-zigs. I just took the carbon chain and I drew it again without the double bond. Keep the carbon chain exactly as it is. Syn-diol addition. So they're both up or they're both down. Right? It's not halogenation, which is anti-addition, syn addition. Are those different products? What's different about them?
Because if you change that chiral carbon, it would become anti, whereas this is syn, so.
Instead of changing that chiral carbon, I think what you mean is if I rotate around,
Yeah.
if I go from zig-zig to zigzag, and we've talked about that how long? Since Unit 2. We've been talking about perspective of these groups. Now you understand why, because it comes into play when we form these products. If I rotate around this bond, the syn groups now appear anti. This wedged OH is going to rotate around until it looks dashed. It will look anti, but it's not about how it looks. It's about how it formed. And it formed syn. So if I rotate this around, my carbon chain will agree but I'll have a wedged OH and then a dashed OH. So how are these two structures related? What's their relationship? They're diastereomers. They're stereoisomers related by one chiral center being the same and one chiral center being different. So they are different products. The stereoisomer of the trans-alkene and the stereoisomer of the cis-alkene give stereoisomer products. So it matters which one I choose. And remember, this question prompted you for forming the meso product. Sorry, I'm never going to say it the way that you guys say it. Which of these products is a meso compound? The one on the left, the one on the right, or both? The one on the right in the box. Because it's in the box. So it must be the right answer, right? Because I certainly wouldn't have any room to erase anything and redraw it if I needed to. What? So can you prove to me that it's meso?
It's achiral with chiral center.
Is it?
That's the definition.
That is the definition, yeah.
It is achiral because it's symmetric, right?
It's symmetric. So you're seeing a plane of symmetry like this? Because remember, with a plane of symmetry, it has two chiral centers.
Yeah. But doesn't that make it meso? It's not symmetric?
If I'm cutting right through this bond,
It's not symmetric. Never mind.
it doesn't even work. I actually added a carbon
Yeah,
to the structure to where there wasn't a carbon.
never mind.
So it's actually not symmetric, although it looks like it is symmetric. But it's as symmetric as
Right.
this, which is not. So and that's actually one of the reasons I wanted to have this, because that's a common mistake, to think it's symmetric, but actually, if you covered up one half and redrew it, it's not the same.
Is that not meso then?
This is not meso.
It's the other one because the RNS has RNS.
This one is symmetric. This one clearly has a plane of symmetry reflecting it. This is a meso product. This is not meso, this is chiral. The idea about RNS and chirality. If you have two chiral centers in your molecule, and you want to see whether they're symmetric to each other or not, and R chiral center is symmetric to an S chiral center. You see the symmetry? They both rotate in towards their plane of symmetry. So this rotation is symmetric to this rotation. If your two chiral centers share the same configuration, they are not symmetric. R is not symmetric to R. There's no plane of symmetry there. And this came up on the midterm, where you guys were given a compound and one of the answers was wrong. So it gave you cis diol, meso diol, and then either 1R2S or 1R2R. Obviously, one of those two options has to be wrong, because those can't both be right. The compound can't both have a 2S and a 2R chiral center. So it had to have been one or the other, and because it was meso, we knew that they had to have symmetry between them. R is symmetric to S, which feels really weird, I know. I think some of you even explained yourself and said R is symmetric to R. It feels like R and R should be symmetric because they're the same, but actually the rotations are not symmetric. R to S is symmetric. Okay, so I need to make some changes because the alkene that I went with my gut with does not work. Here's another way that I would approach this if I were you. And by the way, this is harder than what I usually put onto exams. On my exams, I'm not giving you these like games to play, right? This is class where we get to explore a lot of the details and come up with these questions. Here's what I would have done. I would have said that I know I've been asked to give a meso compound. And to make it meso, I can either do what I've already done. I can draw it in that conformation where it looks meso, or I can draw it in a conformation like this. That doesn't look meso, does it? It's just the wrong conformation. If I rotate it, then it does look meso. But this is a valid version of the meso form. Okay? I don't really like this because I know that this reaction is not syn diol. So I'm going to rotate it into the version, the conformation that it must have formed in. That's what gets us back to this. This still very much meso, and it shows me how the diol appeared syn. What I want to do is work backwards. I want to take this product that I know is the meso form it was asking for, and I want to figure out what the alkene looked like. Well, I know that it had to form in this conformation. I know the bond line had to look like this because that's how the diol appears syn. And I know that the alkene must have been between 3 and 4. If you know what conformation your structure needs to be in, then you know what conformation your alkene needs to have. All right, last one here is acid catalyzed hydration. Because this alkene is symmetric and not unsymmetrical, it actually means that the carbocation could form on either carbon. The carbocation could form on the left, a secondary carbocation, or the carbocation could form on the right, a secondary carbocation. Both are possible, which means I might get structural isomers. Yes, if one side of my structure was structured differently. But because this is symmetric, if it adds to one side or the other, those aren't structural isomers. They're actually just mirror images of each other. They actually are the same thing. If I form a secondary carbocation, I want to stop and consider whether it will rearrange. And I see that this secondary carbocation is adjacent to a tertiary carbon, which is more stable. And so a rearrangement will occur. So my carbocation will be on the more substituted carbon. And that's where the alcohol will form. So the structure of my final product is this tertiary alcohol. Because the carbocation in the mechanism resulted in a rearrangement and the alcohol added on the more substituted carbon.
Why did we use the original structure and not the one in the middle?
Why did we use the original structure?
Like the one you last drew.
Yeah, why
Why are we using this alkene?
didn't we draw it that way?
Well, we didn't know. We took this. We took this piece of information and we said we know there's an alkene between 3 and 4. And then we had that discussion that we don't know if the alkene between 3 and 4 is cis or trans.
But why in the acid catalyzed one is it not?
Okay, I think I see what you mean. It is.
So we could, okay,
Those are the same
that's
molecule.
what I had, that's fine.
Same molecule. Yep.
Why, is there a reason you chose to draw it like that?
Well, just the lowest energy bond conformation. Remember, zigzag is lower energy because everything is anti. Zig-zig is high energy because everything's eclipsed. This is a low energy conformation. This is a high energy conformation.
So would it be correct to draw the lowest?
Nope. You could draw this full points.
In the like middle though, for the starting material, would it be
Yes.
incorrect there?
This alkene is what gives us a meso product.
Yeah.
But the transalkene doesn't give us a meso product. But once again, this is a harder challenge than what I'm giving you on your unit tests, on your exams. This was meant to exemplify part of that challenge. The stereochemistry of the alkene can make a difference. Saray, and then Saray. Was that a hand? Okay. I wouldn't call it hydroxide. Wouldn't call it an alcohol because not all OHs are alcohols. This OH is a carboxyl. Some people do call it hydroxyl instead of hydroxide, hydroxyl or hydroxy. Why do we get 2? Because there were 2 vinylic hydrogens. And some of the notes that we left about oxidative ozonolysis, we said vinylic hydrogens get oxidized to form carboxylic acids. In the example I gave you, I wanted to demonstrate that 2 things are possible. A carbon of an alkene might not have any vinylic hydrogens, forms a ketone. Or it might have 1, and then it forms a carboxylic acid. And we even talked about how it might have 2 vinylic hydrogens, gets oxidized to carbonic acid. Okay, one more example that I want to discuss with you guys quickly. So this illustrated what functional groups can be made, what stereoisomers can be made, but what I haven't demonstrated yet is what structural isomers can be made. If we take a compound like this, trans-2-butene, what? Trans-2-heptene. I did not mean butene. And let's run a simple reaction like acid-catalyzed hydration. First of all, this alkene can't follow Markovnikov or anti-Markovnikov. Despite acid-catalyzed hydration being a Markovnikov addition, hydrogen adds to the carbon with more hydrogens. This alkene does not have a carbon with more hydrogens and a carbon with less hydrogens. This alkene is a symmetrical alkene. Both carbons are equally substituted. So both carbons can form a carbocation. Both carbons can get the alcohol. So there is a product here where the alcohol is 2-heptanol. There is a product here where the product is 3-heptanol. Structural isomerism. These were all examples of stereoisomers, but this is an example of a structural isomer.
Do we always write the isomers in various forms with a plus?
Yeah, oftentimes they're related by a plus sign.
But it doesn't necessarily mean that them together equals that.
Oh, yeah, absolutely. These cannot be undone.
Okay.
Yeah. Now, how many chiral centers are formed in 2-heptanol? 1 chiral center. What stereochemistry will it have when it forms? Why? Why R? So both? Both can form. The carbon started achiral, which means that its top face is identical to its bottom face. So when the alcohol adds, it has a 50-50 chance of adding wedge to the original flat carbon or adding dashed. And how many chiral centers formed on 3-heptanol? one chiral center, with a 50-50 chance of adding wedged or adding dashed. So this reaction also has two different stereoisomers within its structural isomers. Actually, in terms of racemic mixture, you want to define racemic mixture again for us, Michael?
It's like the, isn't it like you have an R and an S group in different quantities in one reaction?
50-50 enantiomers. A racemic mixture is 50-50 enantiomers. So these are enantiomers. Both can form 50-50. These are enantiomers. They form 50-50. These are enantiomers. They form 50-50. But I don't have a good example of diastereomers here. These are not enantiomers, so their relationship definitely won't be 50-50.
So, when you say 50-50, does that mean the potential to form each is 50-50, or in the mixture there's truly half each, half?
It's very strange, but in the mixture, truly, if two enantiomers are the product,
Yeah.
they form 50% of the time. Unless you have a reagent itself which is chiral, and then it gives preference for one version over the other. If you form diastereomers, if, for example, we were to run a reaction that already had a stereocenter, and then gave two new stereocenters, one chiral carbon never changes configuration, and then these other chiral carbons flip, those are diastereomers, and they do not form 50-50. Diastereomers form randomly. There's no way that I would ask you to predict their relationship. Liana?
I have a slightly unrelated question, but on the first example, there's 5 carbons in the chain, and then on the left, isn't that? Oh, never mind. I answered my own question.
You're talking about going this way?
Yeah.
And how the 3 to 4 bond got cleaved, so carbon 3 is over here and carbon 4 is over here. And I will point out, when I mapped these, I didn't number every carbon, but we can keep track of them. 1, 2, 3, 4, 5, methyl off of 3. 1, 2, 3, 4, 5, methyl off of 3. All right, we've got mechanisms to do. So we're going to start with the top mechanism on the left. What reagent is necessary over the arrow to complete the reaction as shown? Before we do the mechanism, what reagent is necessary?
Hydrochloric acid.
Yes. What we see is that a hydrogen and a chlorine have added across the structure, so I need HCl in my reagent. All right. 4 mechanisms that I'm asking you to know. HX addition is the first one. I consider there to be two steps to an HX addition mechanism, but sometimes more than 2. Because some carbocations will rearrange, some carbocations will not rearrange. Does the carbocation in this reaction rearrange? Yes or no?
Yes, this does.
It has to, because there was a tertiary hydrogen that is no longer there, and because my H and Cl have not added across the 2 carbons of the alkene, the Cl added to a carbon that was not part of the alkene, so it has to rearrange. Not every reaction has a carbocation rearrangement. That's why I call the carbocation rearrangement step 1A. Are you guys okay with what I'm saying there? All right. The way that I'm going to demonstrate this mechanism is I'm going to show it step by step. I'm going to show the starting materials in the first step. I'm going to show what they do in the second step. I'm going to show the products at the first step and then start them again at the beginning of the second step. This is what I call step-by-step mechanism. It takes a lot of time because everything you draw as a product, you have to redraw as a starting material. But it leaves things uncluttered because you're only adding arrows to the left side of a reaction. You can do this by a fully sequential mechanism where you draw arrows, draw the intermediate, and then on that intermediate, draw arrows to go to the next step. I'm going to solve this one by stepwise. I'm going to solve the other one fully sequential. So I'm going to give you guys examples of what both look like. Okay, acid-base step is our first step. Why should acid-base be our first step? Well, I'm reacting with hydrochloric acid. So tell me, what's the acid? What's the base? Good. If HCl is the acid, the alkene has to be the base. Were you going to give its name? But it won't start with 1. 3, 6. Okay, so the alkene uses its pi electrons, bonds to the hydrogen. Chlorine takes the electrons back and forms chloride. Does it matter which carbon uses the electrons? No, these carbons are symmetric. They're equally substituted. So they both have a chance of using the electrons, like here, how they both had a chance of using them. But the molecule itself is also symmetric. So either place the carbocation goes to is identical.
On that right-hand side, would you need to show positive charge on the laying down?
Yes. But I'm debating right now which carbon should take the positive charge. Since the molecule is symmetric, it doesn't matter which carbon takes the positive charge. And since I've been shown this structure, I'm going to put the positive charge on the top carbon, which is going to help me draw it just like how it's shown. Yeah?
Would it matter?
It would not matter. In fact, both are possible. And for this reaction, both are the same. So it would not matter. Okay, that's my first step. Now the question is, will this go through a carbocation rearrangement? Yes or no?
Yes.
Why do you know that? Yes, I couldn't understand a word any of you said, but you all said it. Secondary carbocation adjacent to a tertiary carbon. Am I expecting a methyl shift or a hydride shift? Hydride shift. Hydride shift takes less energy. Hydride shift is actually better for our stability. So these electrons move to the right and they fill in the vacancy, leaving behind a new vacancy. My second step, I get that it's actually step 3, but it is the second thing that needs to happen if a carbocation doesn't happen, or if a rearrangement doesn't occur. My second step is a simple nucleophilic attack. What's my nucleophile? Chloride. Chloride has an excess of electrons that it wants to share.
That second hydrogen, that was always there, right? We just didn't draw it.
Yes. Yes, those pesky assumed hydrogens. Draw them in at every step if you want to, because it can get annoying, like seeing that they're not there and then trying to see that they are there later.
You're just showing it now because you're showing that's what's moving.
Correct. I'm only showing it now because it's only relevant now. But you can show it throughout the entire thing. That doesn't matter. You can show it, but I want you to know that a lot of times they will be assumed. Okay, the other example on the top right, does it have a carbocation rearrangement, yes or no?
No.
Why not? There are 2 different carbocations possible. A secondary carbocation could form, a tertiary carbocation could form, because this alkene is unsymmetrical. If a more stable carbocation can form, it's the one that will form. So this has no carbocation intermediate. I would like you guys to try showing the 2 steps for this mechanism. Based on what you've already done, show me the 2 steps. Oh, and what reagent is necessary over the arrow? Hydrobromic acid. Good. You go, Michael. Do you feel good? Perfect. Feel free to check in with others and see if you can help them at all. Looks great. Remember, being able to predict the intermediates is just as useful as being able to show the arrows. When I grade these, half of the points go to the structures, half of the points go to the arrows. If you only know how to predict the intermediates, you can get half the points of a mechanism. The arrows then can just be explained by what's happening at each step. Perfect. Feel like you got it?
So,
Perfect. What did we do with that pi bond last time?
Last time we put it into the hydrogen.
Act as a base. That's right. If you've got an acid, use your pi bond as a base. Perfect.
I was playing catch up with something else that I know.
That's okay. I play Tetris sometimes.
Oh no, I meant with I was.
No, I'm
You're just saying you're smarter than me. I get it.
no, not at all what I was saying. Quinn, you've got it. You're good. There you go. See how you took exactly what we did last time and just showed it.
Goes into here.
Perfect. That's a good start, Kayla.
Is this working so far?
Exactly. This does not happen.
No?
First of all,
Okay.
that carbocation is a secondary carbocation.
I put it there for the first time.
Yep.
Was that right the first time?
Yeah, I don't know how you got a second methyl group there.
Oh, did I do? Oh, I don't know.
You see how there's only one group coming off of it?
Yeah.
So there were 2 places I could have put the positive charge. I could have put it here, or I could have put it here.
It makes more sense here.
It's more stable there.
So then, with this structure, so then with the positive cations,
Mhm.
how do you know whether it'll be with the tertiary or secondary? But it'll be more so with the tertiary because that's what. But it could also be the secondary, but it won't be less stable. So then, would it matter?
If you have the energy to make the secondary carbocation,
Right.
you already had the energy to make the tertiary, so the tertiary is the one that gets made.
Okay,
Does that make sense?
that makes sense.
If I heat these up in a lab and boil them,
Right.
it's going to take more energy to make the secondary carbocation. So by the time that's a possibility, the tertiary one has already formed,
Okay.
and the reaction's done. Who can I sign off still?
Is electron deficient?
Did I sign off on you? Second step's good. Second step's good. Great work.
Electron deficient.
First step is good. The second step is not good. We do not want a carbocation rearrangement here because the secondary carbocation is already harder to form. Instead, it will be much easier to directly form the tertiary carbocation. So the rearrangement won't happen. All right. First step, acid base, looks exactly like our last one. The pi bond attacks hydrogen and bromine takes the electrons. By the way, did you notice I put HBr over the arrow? But to show it in the mechanism, I have to show the bond because that bond breaks. All right, I told you I was going to give you a fully sequential mechanism. So this time, the products that I draw, I'm going to draw arrows onto them. I have two places that I could form a carbocation, one that is less stable, one that is more stable. Where will it go? To the tertiary carbon where it's more stable. This one will not have a rearrangement because the more stable one forms. So there's no 1A. Instead, our next step is nucleophilic attack. Bromide attacks the positively charged carbon. And we're done. That's the end of our mechanism. Easy or hard? Easy.
If the alkene on the starting material was terminal, would there be a carbocation rearrangement?
This is terminal.
No, sorry, I mean like if it was on the last carbon.
Oh, right.
If that was what we were.
Still preferentially forms the secondary, the more stable, more substituted carbon. But now the secondary carbon is adjacent to a tertiary carbon, yes. So it would rearrange. Do you know what this looks a lot like? On the diagram sheets that I gave you,
Yeah.
this is the molecule I gave, which did go through a rearrangement.
Yeah.
And the only difference is just extending that carbon chain. Good. Okay, our next mechanism is almost exactly the same thing we just did for HX addition. But now we're using water instead of a halogen. And we have an extra step at the end. We have to do an additional acid-base step. So we've just finished HX addition. Now we're doing acid-catalyzed hydration. And this is the deal. I want you to think of HX addition mechanism and acid-catalyzed hydration addition mechanism. I want you to think of those as essentially the same mechanisms. They both have carbocation intermediates, which means they have the potential for rearrangements, which means that they're going to share all of the same similar steps. The difference between them is that the acid catalyst needs to be reformed at the end. What reagents go over the arrow here? H2O and H3O plus. Good, water and hydronium. When I show my mechanism, I'm going to show H2O and H3O plus at each step. Am I in acidic conditions or basic conditions? Definitely acidic conditions. If I have hydronium, I'm in acidic conditions. What's my acid? H3O plus. Why is H3O plus a better acid than H2O?
Because it wants to only give up that hydrogen.
Can we use caryo to justify why H3O plus is more acidic than H2O? Charge. H3O plus is more positive. More positive is more acidic. Can anyone justify why my aromatic ring is staying unchanged? Why am I not doing an alkene addition reaction everywhere in my aromatic ring? It's not an alkene. It is different than an alkene. It's far more stable, like Rowan said. The aromatic ring does not react like alkenes because the aromatic ring is not alkenes, despite having a double bond type shape, kind of like the alcohols and carboxylic acids. Share a little bit of similarity, not the same. What's my base? The alkene. So in my first step, I form the most stable carbocation that I can. Do I anticipate a carbocation rearrangement? No. No carbocation rearrangement. It's already as stable as it can get. And I understand that some of you would say, I could make it less stable so that I can show a rearrangement. Why would you do that? So then we move on to the next step, which is the nucleophilic attack. What's my nucleophile? I'm sorry, guys. I know you're catching up. but I did miss something. I didn't draw the water that sits as the byproduct here. For this nucleophilic attack, what is my nucleophile? Water is my nucleophile. And I've got two equivalences right now because the conjugate base of H3O plus is also water. So my nucleophile is water, which means that at the end of this nucleophilic attack, my oxygen has 3 bonds. Oxygen with 3 bonds has a positive charge. Do you guys see why we need a third step? HX addition, nucleophilic attack was it. We were over. Why do I need a third step now? I need to remove one of those hydrogens. We can call this deprotonation. I think on your sheet I said acid-base again. We can call it deprotonation. We need to remove one of those hydrogens from oxygen. There's actually another reason why we can suspect that we need another step. Have I reformed my catalyst? No, my catalyst was the acid, H3O plus. I consumed my catalyst in the first step, and I haven't regenerated it. In order for this to be acid catalyzed hydration, the acid has to be reformed at the end. So here we go. Water acts as a base, gives the electrons back to the new alcohol, reforms my catalyst, and finishes my alcohol formation. I'd like to ask you to never invent steps here. Never combine them. Never try to show this in fewer steps. When we present a mechanism, we are saying, this is how the bonds form and the bonds break. These are the molecules that have to run into each other. These are the places they need to run into each other with. When you change the number of steps, when you change what bonds form and what bonds break, you are changing what you say needs to happen for the mechanism to occur, for the reaction to occur. And I'm telling you, this is how the reaction occurs. So this is how I want a mechanism presented when I give this to you.
So would we get like docked for not including like the extra H2O in the steps or not?
No, that's a good question. So you can see that water is not relevant here. You can see that the second molecule of water is not relevant here. But then you get to this step and you need to add it. So I have a preference for just showing everything that will play a role at every step, even if it doesn't play a role at every step.
I'm sorry, why do we have 2 water molecules?
The acid becomes a conjugate base.
Oh.
So we had both water and acid over the arrow. The acid becomes a conjugate base, water. One of those molecules acts as the nucleophile, the other acts as the conjugate base.
Okay.
And Rowan's question was, do I have to show all of them? No. But I think it's going to make more sense to you if you keep track of them so that you see where they come in. How many other molecules of water are involved in this reaction, by the way? Just like 1 billion or so. Yeah, actually 1 billion is a really small number. This reaction is being run in water, most likely, which means that there are tons of solvent molecules surrounding. We're just paying attention to the ones that actually do anything. Okay, can you draw the mechanism on the right? Will the mechanism on the right require a carbocation rearrangement?
Yes.
How is that evident?
Because of what alkene is talking
Not just because the alkene is terminal.
But if it breaks, there's a more substituted one to the side.
There's a carbon that moves. Sorry, that's what I was looking for. A methyl group has shifted in this structure. You see how it looks like there's a tert-butyl group in the starting material, but there's absolutely no tert-butyl group in the product? Elvira is looking at the patterns. She's finding them. She says it's terminal, which means I've got a secondary carbocation possible, and it's adjacent to a more substituted carbon. Perfect. But also, just at a glance, a methyl group is moving. That's going to have to require a carbocation rearrangement. Okay, show me how to solve this one. Use this as your template. Do not deviate. Do not make changes. Just change the carbon structure. I'd like to come around and give advice if I can.
I want advice.
Looking great.
Okay, but is this where I put my, where do I put
You have
my-
two options for where the carbocation goes. Either the
Not
alkene
here.
carbon on the right or the alkene
and
carbon
this
on the
that'll
left.
go here.
It'll go to the more substituted. Yep. Now that you've formed a carbocation,
Then I can do the other one.
exactly. That's why the rearrangement is step 1A after it forms. Yep. But you just haven't shown the arrows for it. So this is what I mean when I say you'd get partial credit in your mechanism because your intermediate is correct. It's just no arrows. Yep. And also your positive charge. Great. Yes. Perfect. You're exactly right. Now, will it rearrange?
Well, where could it go?
Well, you have a more substituted carbon to the left.
Isn't it full though?
Maybe you could map your carbons and figure out if any groups need to change.
Why don't I try that?
Yep. Yep, exactly right.
But then, like, wouldn't this also be positive for the OH2 attached to it?
Well, I agree. So this is where I just told Elvira, maybe you can map your carbons to figure out what change needs to happen. The question now is, will there be a carbocation rearrangement or will there not be? Looking great. Is that carbon on the left holding the positive charge? Because that carbon on the left
Wait.
is not involved in the alkene.
Oh, right, it has to be involved in the alkene, but it has to be the most highly substituted. Okay.
Good.
Perfect.
So if you're starting at
Okay.
mapping, this would be 1 because it gets added on to your OH would be.
Well, that's not a carbon. So if this is how you've mapped it, 1, 2, 3, 4, then I would say maybe 1, 2, 3, 4,
Okay.
right?
So this does not have to end up attached. Okay. Oh, because that's not a carbon. I see what you're saying. Okay, and so then.
Positive charge on H3O plus.
Yeah.
Good.
Okay, so then.
You've got it.
Because the methyl has to move.
Alkene acts as a base. The alkene doesn't exist. Right? It looks like it's drawn in, but it's not supposed to be. Is that correct? And then you've shown a methyl shift, but you haven't shown me the electrons for a methyl shift. Okay. You're on the right track. You're on the right track. Now the question is, how do I do a rearrangement?
How do I swap the methyl and the carbocation?
So the carbocation is a vacancy
Yeah.
that the methyl group can shift into. So we show the arrows point toward the carbocation.
So like that?
Yep, just like that.
Oh.
No lone pair. I want to see the lone pair that attacks.
Oh, okay.
because it's not the nucleus
It's not the actual, yeah.
that's bonding, it's the electrons that are bonding.
So just so it would include something like this.
Perfect. And then you do the same thing here.
Where
Do you agree that your arrow is pointing
the right way.
the wrong way?
Oh, this, yes. you're
It
right.
has to. It has to.
Yes, I do agree, I'm correct.
It
So it appears
Like that.
yes.
And that's good.
Perfect.
so they kind of just swap spots.
The carbocation doesn't swap.
Well, it's just a big
That's like
thing, so it's like
yes.
a whole-
That's like saying when I step forward in the TSA line, did I swap places with the gap in line? No, I actually created a new gap behind me
Okay.
by filling into this gap. It looks like the positive charge is moving, but it's things moving around leaving a new positive charge. This is exactly what has to happen.
Okay.
So how do we add arrows that say
Oh, right.
one of these methyl groups is moving? And then that's down there is great.
Can I just literally draw an arrow?
Yep. Your alkene is not pointing its bond at a hydrogen. Notice how here the alkene bonds to hydrogen?
That's just bad drawing, but yes.
So and that's where you'll have to focus then on the detail. Where is it pointing to? All right, now the alkene's bonding to that hydrogen.
Mhm.
Can that hydrogen have two bonds? You see what I was getting at? The hydrogen that gets attacked by the alkene is the one that has to break its bond to O.
I've erased a lot of this multiple times, so I just mix up where I draw.
Perfect. I think the only thing is the positive charge is not obvious down here.
Oh,
Maybe-
that's because I didn't write it.
okay. But otherwise, great.
I think the way that I did this, I'm gonna end up with my OH group on this.
That's okay. You see how this molecule's
flipped?
flipped? Yeah. All right, I'm gonna start solving this for you guys.
Can you check mine really quick?
Yes, I can. Perfect. Yep. Can you say that again?
In these reactions, we always start with hydronium and end with hydronium.
Yes, hydronium is our acid catalyst. Yep.
So we don't consume it, we use it and then end with it again.
Yes, yes. Use it and then remake it. Okay, so here's my acid-base step. My alkene acts as a base. It becomes protonated and forms the most stable carbocation. And then a methyl group shifts over. That's because the methyl group is the smallest thing that can shift over. There is no hydrogen to shift. But also, if you are mapping your carbons, then, and it doesn't matter how you map them, but you'll notice that carbon 3 had no methyl group coming off of it, and in the product it does. You'll notice that carbon 2 had 2 methyl groups coming off of it, and in the product it only has 1. So we're seeing that a methyl group has to shift. And that's what we see here. The methyl group shifts. Water acts as the nucleophile. Now, a lot of you were doing this well earlier, but I want to point out, water acts as a nucleophile because of its lone pair. So the arrow has to come from the lone pair. We get to assume lone pairs, but this lone pair is relevant to the mechanism, which means you cannot assume it. You have to show that lone pair. What that does is it creates this 3-bonded oxygen, a positively charged oxygen, just like we had last time. And so unlike HX addition, now I need to show a deprotonation step. And then I have my final product.
So we came to the whole methyl group. Okay.
Yes, we move the whole methyl group. How many points do you think that I should grade this mechanism out of? I assign points for mechanisms based on the steps involved. So this mechanism, where'd it go? This mechanism was 3 steps. So this would be a 3-point mechanism, or a 6-point mechanism, or a 1.5-point mechanism. but the number of steps is related to the number of points that I'm going to base it off of. This was only a 2-step mechanism, so that might be 1 point, that might be 2 points, that might be 4 points. 2 steps, so I'm going to base the number of points off of that. And then I'm looking for, do your structures agree and do your arrows agree? Here I've got 4 steps, so that's a 4-point mechanism, a 2-point mechanism, an 8-point mechanism. Make sense? Rowan?
So if you're gonna make like a mistake early on, but then you were like consistent with that mistake,
Mm-hmm.
you still get points.
It depends on what your mistake is. Like if your structure is wrong, you lost a methyl group, or maybe you added too many carbons in your chain. That's usually some points off the mechanism, but not at each step, because that's a consistent mistake. Did that answer your question? Yeah. All right, we have 2 mechanisms left. We have the halogenation mechanism. How many steps is the halogenation mechanism? 2 steps. Who said 3?
I was guessing.
Oh, okay. I'm going to give you guys the reaction on the left. What do we know about halogenation and the stereochemistry that it gives? Halogenation is an anti-addition mechanism. So why do they look cis?
Because they're rotating.
The bond, the carbon chain has gone through a conformational rotation. Do you see how the alkene is cis? So it's a zig-zig conformation, but the product is drawn zigzag. Let me draw the product as if it had remained in that zig-zig conformation. And what do we get? We see why it's an anti-addition mechanism. We see the conformation it formed in. Which of these do you have to draw? Either one, because they're the same molecule. Doesn't matter. What reagent goes over the arrow? Br2. How do you know it's not HBr? There's no hydrogen added. There's 2 halogens added. That's Br2. All right, the first step, I call this the bromonium ring formation. In fact, it doesn't matter which halogen it is. We can call it the halonium ring. You guys have done this mechanism, by the way. When we practiced our mechanisms, I had you guys practice the arrow pushing on this. The alkene acts as a nucleophile, and it attacks one of the bromines. That same bromine that gets attacked by the alkene attacks the alkene back with one of its lone pairs. And then the bromine-bromine bond breaks to form bromide. Do you remember practicing this mechanism and how challenging it was for you guys to predict, how do I make both of the bonds between both carbons and one halogen? Now you know. All right, we know that there's some stereochemistry here. This ring, much like an epoxide, either forms on the top face or on the bottom face. So it can do both, and I've decided to show it forming on the top face.
What do you mean by top face?
Top face of the alkene. Alkene's flat, so the halogen can either form on the top or it can form on the bottom. And I'm saying it's forming on the top. It could form on the bottom, and actually either way we can get to our product. Here's my bromonium ring. And my bromonium ring goes through a backside attack. Like a nucleophilic attack, the backside attack inverts some stereochemistry. That's why we call it the backside. The nucleophile, bromide in this case, will attack one of the 2 carbons of the ring, and it will open that ring. So this backside attack, we could also call it ring opening. If bromide opens the ring, it has to attack from opposite where the ring already is. That bromine is sitting on top of those two carbons, and so bromide has to attack opposite it. So if the bromine already present is wedged, the new bromine is going to end up dashed. In other words, anti-addition, backside attack. Which carbon of my alkene, or sorry, which carbon of my bromonium ring should bromide attack?
Either one, right?
Doesn't matter because they're equally substituted. If they were not equally substituted, which one should it attack? Why? Why attack the least? More room, less steric strain. But actually, when it's more substituted, when one carbon is more substituted, the bromine or the chlorine will stretch the bond, meaning that there's more of a positive at the more substituted, where we know more positive happens. So the bromide will always attack more substituted. On active, this is important. Active will only give you the correct answer if you have it attack more substituted. So it attacks more substituted. Which is more substituted here? Neither. Okay, what about this though? I want to form this product. This was the stereoisomer given to me. I want to form this stereoisomer. Which carbon should the bromide attack? The one on the right, because the wedged bromine needs to be on the left, and the wedged bromine is already there. The backside attack will give me a dashed bromine, and I want that to be on the right. Here's something that happens a lot. I'll see students attack one carbon of the ring, but break the bond from the other carbon. They'll attack this carbon, but break this CR bond. You can see the problem there is that you don't actually conserve octets the way that you need to. All right, now I told you either of these conformations is perfectly legal for the final product, so I suspect most of you would end up drawing it like this, and you're done. That's your electron arrow pushing mechanism. I want you guys to do that next one, but I'm running out of time. So I'm going to take you guys through the Halohydrin, Haloether mechanism, which is nearly identical to this, except that the nucleophilic attack, the backside attack, is not done by bromide. Instead, it's done by either water as a nucleophile, and then water has to be deprotonated, or alcohol as a nucleophile, and then alcohol has to be deprotonated. So you'll notice that, once again, Halohydrin, Haloether is anti-addition mechanism because of the backside attack. But Haloether, Halohydrin both require that acid-base step. Just like how the acid-catalyzed hydration required acid-base that HX didn't, Halohydrin, Haloether requires acid-base that halogenation doesn't. They are nearly identical mechanisms. Just that last step is different. Which one would you like to see? The reaction on the left or the reaction on the right? On the right. Taking 2-methylpropene and making 1-chloro, 2-methyl, 2-methoxy. What reagent do I need over the arrow? Cl2 and OH.
Yeah, like an aldehyde.
No aldehyde.
Just an OH.
Water will not get me a methyl group. O2, oxygen. OCH3. What I want you guys to recognize is that on this diagram on the front, where you have halohydrin and haloether, halohydrin forms X and OH. Water is the reagent. Haloether forms X and OR, ROH is the reagent. I'm forming an ether. So I need an alcohol that will become that ether. I need an alcohol that has that R group, CH3OH. That's as simple as it is. Whatever ether I have, that's the R group that my alcohol has to be. All right, step 1, halonium ring. It doesn't change. Well, this time it's a chloronium ring. Once again, I'm going to draw each of my reagents, even if it's not relevant at a given step. My alkene attacks my chlorine, and my chlorine attacks back. Can you predict which carbon chlorine will attack? Yes, chlorine attacks the more substituted, because the more substituted is more positive. And you always send electrons to where there's a more positive charge. I form my chloronium ring. And this is where I want to highlight this chloronium ring is asymmetric. It's stretched significantly away from the more substituted carbon, giving that a bigger partial positive. Do you know what? This one I'm not going to do step by step. I'm going to do this one fully sequentially, okay? Second step here is backside attack. What should be my nucleophile? Last time, Br- was my nucleophile. So this time it would stand to reason chloride should be my nucleophile. But wouldn't that just give me a halogenation product? It wouldn't give me an ether. So what else should be my nucleophile? It won't be chloride. The oxygen of my alcohol can be a nucleophile. It's got that lone pair. Which carbon of the ring should it attack? Attack the more substituted. So methanol, from its lone pair, attacks the more substituted carbon and opens the ring. Did anything happen to the bond between oxygen and hydrogen? No. So that bond between oxygen and hydrogen is still present. Remember when I asked you, don't invent new things to these mechanisms? I've had students that will take this 3-step mechanism and they will make it 1 step. And they'll show all of the bonds forming and breaking at the same time. Don't presume that. That is saying all of this change happens at once. It's not plausible. What's plausible is that these things happen incrementally. First, oxygen acts as a nucleophile. Then, chloride deprotonates the oxygen. There's that deprotonation step, or the way that I put it on your sheet, acid-base chemistry.
Is there a reason that CH3OH attacks as opposed to the?
Good question.
Or is it just because we have the product?
There is that off chance that chloride does attack. So if you ran this reaction, you don't get 100% yield. You have 5% halogenation byproduct.
But since we have the product, we just
But when you're running this reaction, methanol or water or any alcohol is your solvent. So you've got, I only drew one, but we've got 1 billion or more of them. Chlorine is drowned out, essentially. And that's what I like to say here, is that it essentially becomes too diluted.
Like that extra charge from, oh yeah, okay, you show it.
I didn't show it. Yes, I meant to. HCl. But there is methanol that could act as the base. And in reality, methanol is a better base than chloride. I am giving you this mechanism, though, because this just makes use of everything available. And so it should feel more intuitive when you're trying to solve it on your own. This weekend, your unit test will have you answering questions like what reagent is necessary, what structural isomers are possible, what stereoisomers are possible. And on your part B, you will be solving a mechanism. You'll have different mechanisms to solve depending on which question you get, but all of your mechanisms will have the same steps, the same number of steps, because I have to assign them the same number of points. And I can't give someone a two-step mechanism out of 3 points and someone else a three-step mechanism out of 3 points. So even if you have different mechanisms, know that you're doing the same number of steps.
So this will be part B.
Part B, your written work.
So when we're looking at this, like with the sheet that you gave us, for
Yeah.
those 12 reactions, like for part B of the unit test, it's safe to assume that it's going to be from that, right?
Yeah.
Okay.
Do you know what? I think my camera died. But it's fine. I've done these mechanisms for a while, so there's.
You're in person.
Yeah. Mm-hmm. Okay. Have a good weekend. I'll see you guys next week.